Hey there, welcome to my channel. In this video I'm going to talk about dark matter and dark energy, which makes up 95% of the universe, yet we can't see any of it. So let's get started with part 1. What is dark matter? I am a NASA astrophysicist. As a NASA astrophysicist, I spend my life studying the universe. But here's the truth. 95% of it is invisible to us. I know it sounds crazy, but let me show you what I mean. Have you ever seen a spiral galaxy like this one? Well, if you watch long enough, you might notice something strange. Everything in the galaxy seems to be flying apart. Stars orbit the center of the galaxy at incredible speeds. If I were a star in that galaxy, I would be flung into outer space. But somehow, these galaxies stay intact. Why do they stay intact? It's because there's an invisible glue that holds them together. We call it dark matter. It doesn't emit light. It doesn't absorb radiation. Yet it makes up 27% of the universe. This might be a good time to point out that while we know dark matter exists, we don't know what it is. Scientists have proposed many ideas, but none has been confirmed. The leading idea is that dark matter consists of some exotic type of particle. But again, we don't know. So how do we know dark matter exists? Let's move on to part 2. How we know it exists. When you look up at the night sky, you're seeing light that has traveled billions of years through space to reach your eye. Sometimes when light travels across the universe, it takes a detour. And I'm not talking about the twinkling of stars due to atmospheric distortion. I'm talking about a much more extreme effect called gravitational lensing. For example, in this image, you're seeing light from a very distant galaxy, but that light didn't travel in a straight line. Instead, it bent around a massive object in the foreground. That massive object is this huge cluster of galaxies. You see, massive objects warp space around them. Technically speaking, they create a dip in the fabric of space. Normally, that wouldn't affect light passing nearby. But the deeper the dip, the more massive the object, the greater the effect on light. In the case of this galaxy cluster, the dip is deep enough to bend light. And because the distribution of mass in the galaxy cluster is somewhat lumpy, the light gets distorted into a smiley face. We know this effect must be happening because no light source is actually in the shape of a smiley face. Also, we can tell from the color of the background galaxy that it's very far away. Otherwise, we'd be seeing a blue shift or a Doppler boost in its color. Because of gravitational lensing, we're seeing not just one background galaxy, but several images of the same galaxy. We know the real galaxy isn't shaped like a smiley face. So the only explanation for this observation is that the light has been bent around massive objects. And where is that mass? Well, we can't see most of it. It's not stars, gas, or dust, because those things are transparent to visible light. Instead, it's dark matter. Let's move on to part 3, dark energy, the force of expansion. The first part of this video showed galaxies orbiting around a central point, held together by dark matter. But what if I showed you this? What are these galaxies doing? They're flying apart. In fact, they're moving away from each other faster and faster. And this isn't just happening in this one patch of space. It's happening everywhere. The entire universe is expanding. So you might think the universe is getting bigger. And that's true. But the universe isn't just getting bigger. Space itself is being pulled apart. Think about it this way. Imagine you have a bunch of dots drawn on a balloon. Now imagine blowing air into the balloon. As the balloon expands, the dots move apart. This is analogous to the universe. But why are the dots moving apart? Is there some force pushing them apart? Indeed there is. It's dark energy. In the 1990s, astronomers discovered that the expansion of the universe wasn't constant. It was accelerating. So this means that dark energy must be growing stronger with time. It's weird. As the universe grows, dark energy grows. So far, the best explanation for dark energy is that it's a property of space itself. Think about it this way. If you pull two people apart, you're doing work and increasing their potential energy. Space is kind of like that. As it expands, dark energy is being stored in the newly created space. So the more space you create, the more dark energy you have. But that's just a model. Again, we don't really know what dark energy is. Let's move on to part 4, Why it matters. Everything you see around you is made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks, and quarks are elementary particles. That is, there are no smaller constituents of quarks. For all we currently know, everything you see in the universe is made of less than 1% of the particles populating the universe. So then what is the rest of the universe made of? Well, we know the answer, but it's not exactly satisfying. About 27% of the universe is dark matter, and nearly 70% is dark energy. Right now, dark energy is winning the battle of the cosmic repulsion. That is, dark energy is pushing things apart faster than gravity can pull them together. But will this always be the case? Perhaps. But perhaps not. Let's run a simulation to find out. In this simulation, I've colored dark matter in red and dark energy in blue. You can clearly see that dark energy is causing the universe to expand. But as the universe expands, more dark matter is created. This is because dark matter is a form of matter, and new matter is created as space expands. As space expands, more dark energy is also created. But dark energy isn't like dark matter. It doesn't clump together. Instead, it fills all of space evenly. Because dark energy is clumpier, it's able to overcome the repulsive force of dark energy. Gravity pulls the universe together, causing the expansion to slow down. Eventually, gravity wins the battle of the cosmic repulsion. At this point, the expansion of the universe is completely halted. But gravity doesn't stop there. It continues to pull the universe together. At this point, the dark side of the universe begins to collapse. All the galaxies are swept up into huge cosmic pancakes. These pancakes collide and break apart, creating a cosmic soup of dark matter and dark energy. But the story doesn't end here. No, the cosmic soup is hot enough to create pairs of exotic particles that fly off in opposite directions. These particles are the seeds of the next universe. Where did they come from? Well, it doesn't matter. What matters is that the Big Bang is about to happen again. It may sound a bit dramatic, but this is science. We're dealing with singularities, points of infinite density, and we're talking about the curvature of space-time. Not even physicists really know what's going on in such conditions. So, the question still remains, what will happen to the universe? Will expansion continue forever, stretching galaxies into isolation? Or will it slow down, and will everything collapse back into a cosmic big crunch? We simply don't know. Which brings us to part 5. NASA's search. At NASA, we use telescopes like Hubble, James Webb, and soon the Euclid mission to search for clues. For example, Euclid will measure how fast the expansion of the universe is changing. With this measurement, we could determine whether the expansion is speeding up or slowing down. If it's speeding up, that could mean dark energy is growing stronger. If it's slowing down, that could mean gravity is winning the battle of the cosmic repulsion. Either way, every discovery brings us closer, but the truth remains hidden. So the next time you look at the stars, remember this. Everything you see, planets, stars, galaxies, makes up less than 5% of reality. The rest is dark matter and dark energy, the greatest mystery of our time. Would you like me to reveal what scientists believe will happen to the universe in the end? Stay tuned, and thank you for watching.